Dr. Justine Garcia, with the title of her HU talk as "Will Monkeypox Be the Next Epidemic?" So go ahead, Justine, the floor is yours.
Okay, thank you. I'm going to ask one favor, which is that the internet in my office sometimes randomly goes wonky. So if I get real quiet or frozen, please let me know so I can stop and try to adjust. Otherwise, let me share my screen and we'll get started. Okay, I did put pandemic on here. So really what I'm trying to ask here, and I think anytime now someone still hears in the news emerging viral threat or global spread of virus, it's very triggering. So what I really want to be doing here is saying, is monkeypox going to be the next COVID-19? And yeah, spoiler alert, it's mostly a no, but there are some important things to sort of differentiate and understand about monkeypox. So if you have purposely been ignoring the news or living under a rock, over the summer, we had headlines like this, where we saw monkeypox outbreaks popping up all over the world. Monkeypox is endemic, meaning it's sort of normal in about 11 countries in Central Africa. And so we started to see them in Australia, Belgium, etc. And you can see the date here is sort of end of May. So this was over the summer. Then we got other things like monkeypox identified in the US, monkeypox identified in the Philippines. And where we are as the summer progressed, this is in July, but this is where we are now. The WHO declared the highest alert, which is a global health emergency, not pandemic, but a health emergency over monkeypox outbreak. So I want to start today by saying, what the heck is monkeypox? What's going on? Where are we? And then we'll talk about its pandemic potential. So I got this US case count from the CDC yesterday afternoon. So this is quite updated. And as of right now, we've had almost 22,000 cases in the US. New Mexico, we've only had 3. So we're one of the colder spots, but there is cases in the US, there is transmission within the US, and here's kind of what that looks like on a global scale. So we have a pretty big orange dot. Orange means this is not a place where monkeypox normally spreads or is endemic. The blue spots is where monkeypox normally lives. So this is sort of restricted to the sort of middle jungly area of Africa, but you could see now it's everywhere. And looking over the whole world, there's been about 58,000 cases. So we've had about a third of those right now. And mostly they're outside of the cases or outside of places that have historically had monkeypox. So only 511 of these cases have been within sort of this blue dot zone. So this is definitely a spread beyond what is normally seen from monkeypox. Normally, we don't hear about monkeypox in the news. It does spread every once in a while, but something's going on. So where we at now, US has confirmed cases as early as May. We're at about 22,000 now. We've declared a national health emergency. The WHO declared a global health emergency. I just want to point out that sort of an alert status, but it doesn't have the word pandemic in it. So it needs, more is an alert to public health officials, right? Like, look, this is happening. You need to be aware. You need to teach doctors how to recognize these cases, and we need to put a stop to it, but not necessarily we need to lock down the country right now. So first, let's take a little tour in the history of monkeypox. So what the heck is this? Where did it come from? Why is it blowing up now? And then we'll take a look at these 4 characteristics that really determine whether something has a pandemic potential, and I think it will largely be reassuring. So monkeypox is a virus. It's a DNA virus, which will be important later, and it's closely related to smallpox. So Brandon mentioned chickenpox. we'll see all of the pox causing viruses aren't necessarily related, but it's actually really lucky for us that it's related to smallpox. I know that doesn't sound like a fortunate event, but it is. So here's a picture of it. It's sort of a large virus and it has sort of this like bricky rectangle shape. So it's interesting because it's actually one of the larger viruses, and we know a lot about it because we know a lot about smallpox. So here I want to give you sort of an idea about how all of the viruses are related. So first, again, monkeypox is a DNA virus, and viruses are largely categorized by whether their genes are encoded by DNA, like ours are, or by RNA, which no other thing is. Viruses are special in that way, and they can have genes encoded by RNA. They're really, really simple structures. We don't even call them cells. They're just sort of this cobbled together cluster of proteins and nucleic acids. A lot of biologists consider them to be not alive. I think that's debatable, but they're extremely simple. They must have a host to reproduce, so they don't really live on their own. They can't eat food. They can't do anything unless they have a host. And here's the big sort of classification. So when we're talking about monkeypox, we're talking about this big old virus up here in the DNA classification. Smallpox is in that pox virus family as well, but there are other pox viruses. So over, oops, I'll get to that in a second, but I just wanted to point out before the other pox viruses, this is where the coronavirus is. And it's important to notice that it's in the RNA group. So RNA viruses have a lot of special qualities that are really tend to be bad for us. So first sort of reassuring note is this monkeypox is in this DNA family, and it doesn't have these sort of special bad qualities that coronavirus does. So now I'm going to look and show you these sort of family trees within the pox virus family. So if you've ever seen a family tree, it either climbs up or climbs down. This is sort of a family tree just turned on its side. So the closer something is to another thing, the more related it is. So for example, these two little things are really related because they share a branch. And so here are all of the different pox viruses. And the one we're going to be looking at today are the orthopox virus. This contains both monkeypox, there's our friend monkeypox, as well as smallpox. So you'll notice its real close sort of cousin is this virus that we use to make the smallpox vaccine. It doesn't cause smallpox, it's closely related. And then here, the variola virus is actually what causes smallpox. And you notice a few other things if you look at these two little family trees. There's a lot of other animal names: cowpox, raccoon pox, cervid pox, which is deer, squirrel pox. So this has a lot of relation to animal transmission, which will be important as well. But right now you should know it's very, very similar to smallpox and the vaccinia virus, which we use. It's sort of a weaker version of smallpox. So going back to our family classification of all the viruses, there's our big pox virus family we just talked about. And chickenpox is not in that family. So chickenpox is actually over here in the herpes family. And all of these things sometimes that have these pox names really just refer to common symptoms. So a pox is any sort of gross, disgusting rash that has sort of this pus or blistery looking shape, and that ultimately leaves sort of a pock mark. So if you had chicken pox as a kid, and I was sort of in the last group of kids that did have chicken pox because there's now a chicken pox vaccine, so my kids got that. So if you were, I guess, lucky enough to have chicken pox, you might have some leftover sort of little scars. And that's the same thing that happens with both monkeypox and smallpox, although they tend to be much, much worse. But the big takeaway message here is just because something has pox in the name doesn't mean it's closely related, or that we can take the lessons or similarities from those diseases and apply them to monkeypox. Luckily, smallpox is related to monkeypox. Okay, let's move on from the poxes and talk about animals for a minute. So both monkeypox and all of these other pox virus families or orthopox viruses are what we call zoonotic diseases, meaning they transmit and are present in animals, and there can be animal to human transmission. So if you look at this global map here, we're looking at both the smallpox virus in blue, monkeypox in this sort of maroon, and cowpox in this orange. And then where each human is, there's sort of a family of different animals that serve as reservoirs for all these viruses that we humans can get the viruses from. So over here where you see monkeypox in sort of the Central African region, down here we have a lot of little friends like squirrels, monkeys, hedgehogs, other small furry mammals. But you'll notice like almost everything gets these viruses. Over here, there's horses, pigs, cats, dogs, bats, rabbits. These are very, very common viruses that are circulating in animals, and we just happen to get them by interacting with animals. And so places where there's a lot of farms or incursion into the jungle or bushmeat trade, there's a lot of animal to human transmission of these diseases. And you'll notice this has a little bit of monkeypox sort of in North America. This was before the current monkeypox outbreak, but sometimes there are imported cases from animals being moved around the globe. And so monkeypox is not quite like COVID in that it's not a novel virus. We've known about it for about 70 years. So it was first discovered in lab monkeys that were being used in laboratories in the Democratic Republic of Congo in 1958. So that's where its namesake is. It can be in a lot of different animals, but it was first discovered in monkeys. So it's called monkeypox. But monkeys are probably not really its natural hosts. They're probably more present in rodents all throughout Central and West Africa. So here I have a dormouse on the top, super cute. On the bottom, a rope squirrel. And then I put this picture intentionally. This is a giant African pouched rat. And here, these are the rats that can sniff out landmines. So here, this is a trained rat that's on a little leash where it can sniff out landmines. These are cool for a whole other reason, but they can also host monkeypox. So anytime people come into contact with these small rodents and sometimes monkeys, there's a possibility for transmission of monkeypox. And it wasn't just sort of new in 1958, it's probably been circulating in all of these animal populations for thousands or millions of years. Oh, do they have symptoms? That's a really good question, Brandon, because actually this is still, I have a probably here. It's actually really, really hard to find the monkeypox virus in these animals, and it's only been isolated like once or twice. So it seems like they probably don't have these big gross lesions like we get. They might be sort of a little sick, but you'll see in a second, I'll show you some gross lesions. They don't look quite like that. So it's probably not super obvious that they are sick. So here's the gross lesions. So this is what can happen when we get monkeypox. Usually the illness starts out really flu-like. So you get a fever, headache, muscle aches and chills. You can get respiratory symptoms where you're sneezing, coughing, and you get swollen lymph nodes. So this virus actually goes and infects your lymph nodes. That's how it's dispersed throughout your body. And eventually it comes up to your skin and infects your skin. So after you get this flu-like symptoms, you'll start to get these rashes. Not everyone gets these. It's really variable how many of these sort of little rash pustules people get, or rather they get them at all. But if they do show up, they're about 1 to 3 days after the other symptoms, and they start really on the hands, feet, face, and genitals. They're actually really, really painful. They're like these open sores that are sort of achy and oozing. It's pretty gross. This was like the least gross picture I could find that still illustrated how horrible this is. So you might just feel a little bit under the weather for a while, but eventually you're likely to get these sort of gross open sores. And these gross open sores is how a monkeypox is really spread, which I'll get back to in just a second. So we have this huge outbreak right now, but there have been previous monkeypox outbreaks over the last 60 or 70 years. So since the 1970s, there are small outbreaks in the sort of 11 equatorial African countries, and it's largely tied to either people feeding their families through small game or bushmeat trade. I really like this picture because this kid looks so proud of this animal he's killed, but you can think people are living in villages, farming, hunting, in a much closer contact than where we are. And then there was an outbreak in the US in 2003 linked to the pet trade. Apparently, did not know this. Some people like to keep prairie dogs for pets, and some prairie dogs had been housed with those giant pouched rats that sniff out the landmines. And so they transferred it, and there was an outbreak between 70 people in the US. But importantly, these outbreaks have been limited because there's primarily been animal to human transmission, not a lot of human to human transmission. So these are sort of self-limited. Once people remove themselves from the animal source, the outbreak stops. So what's different now? The big difference is we don't just have animal to human transmission, we're getting this part of the equation now, where we have sustained human to human transmission, which is never good, but I think it's not as bad as it could be. So I want to start moving to like what's going on now and what's going to happen in the future. So I want to really look at the potential for this monkeypox outbreak to turn into a pandemic or sort of endemic infection, similar to what we've seen with COVID. So I'm going to do some comparisons to COVID over these 4 parameters that really determine a pathogen's ability to become like this super pathogen, right? A pandemic pathogen. And those 4 parameters are contagiousness, the way it's transmitted, what we know about it and how we can treat it, and then how fast or in what way it evolves. So let's start with contagiousness. And in general, for any pathogen, we have a special number that we use to measure a pathogen's contagiousness. It's called R0 because it was invented by some British scientists. You can call it R0. And what this is the basic reproduction number. So R stands for reproduction, and 0 stands for at time 0. So when this infection or outbreak just gets started, how many people can one person with this infection go on to infect? So here is a little diagram of what that looks like. We're going to look at a pretend pathogen with an R0 of 2. So this one person can infect 2 people, and then each of these 2 people can infect 2 people, and so on and so forth. And that's how you get that exponential spread we saw a lot during COVID, is you have this really contagious thing where each person can be responsible for more than one additional infection. And that's what really allows the outbreak to grow. So here's sort of our scale of what we know about contagiousness. Over here, you might be surprised to find one of the, I think, scariest diseases, Ebola. It's not that contagious. So each infection only results in 1 or 2 more additional infections. So Ebola is really scary because it's quite fatal, but it's not very contagious. SARS, which is closely related to COVID, is around 2 to 5. So is HIV. And then we go up, we have smallpox. So we'll be thinking about smallpox and monkeypox. It's quite a bit more contagious. One person can infect up to 7 more people. And then over here, we're on the really, really contagious end of the spectrum with whooping cough. And I always like to ask, does anyone have a guess for this basically most contagious disease with an R0 of about 18? You can yell it out because I can't see you, or if you want to put it in the chat, I welcome your guesses. What is this disease right here? I have common cold. Any other guesses? Ooh, I see someone was in my class already. So Preciosa guessed measles, and it's measles. Yeah, major cheat. So that's why you hear also about, yeah, common cold is actually way over here. It's not that infectious, surprisingly. That's why you hear about these measles outbreaks like in the Amish community or Disneyland. It is so infectious, even with a vaccine. If one person gets measles, it spreads like wildfire. And so, I keep losing my clicker. Monkeypox is about, hold on. Whoop. Actually, I'm going to come back to that. Sorry, that was a little tease as well. Here's what we had for COVID. And we saw a lot of evolution with COVID, as you could see by how we moved through the Greek alphabet, Delta, Omicron, Alpha, all of that. So the original virus that started in Wuhan, China was about 2.5, which is already kind of moving up beyond like the common cold or even flu that happens every year. And then old figure, we don't even have Omicron on here, but by the time we got to Delta, we were already up to 5 to 8. And so that's why COVID has really been able to sustain itself. It has evolved to have a higher transmission rate and to become more infectious. So it started out not too bad. It's gotten worse and worse as we've let it evolve. So here, there we go. Monkeypox in previous outbreaks, so those small little ones in Africa or the one that happened in the US, were really small. So around 1/2 to 1. So 1/2 means that even every person who's infected didn't even infect another person. And that's really what we want to see. But our current outbreak is a little bit higher. So it's about 1 to 2.5, which is about where COVID started at. And the reason we really care about this is we can use this number to predict what will happen in the future and to implement and see how good our mitigation strategies are doing. So if we want a pathogen or an outbreak to die out on its own, that R0 value must be less than 1. So in other words, you're saying that every infection doesn't even result in another infection. Anytime that R0 is greater than 1, so each person at least replaces him or herself with in the infection pool, the infection will keep growing. It will be amplified. It might be exponential growth, but the outbreak will be sustained. If it's just right at =1, it will kind of limp along forever. So what we really want to do, and what all of our masking, vaccination, social distancing efforts were in COVID, were to drive R0 to below 1. And so some of those are options for monkeypox as well. But overall, what we see for contagiousness in monkeypox, it's not as contagious as COVID-19, especially our current and previous variants that really cranked up the contagiousness. But it is still contagious enough that it could sustain spread for a while. So it's something to keep our eyes on, but definitely nothing like COVID. And I think what will be really a little bit more reassuring is when we look at transmission route. So let's do that real quick. Here's some more awesome lesion pictures. And like I mentioned before, these lesions are really what's responsible for transmission, and it's largely skin to skin contact. So you need to have direct contact with one of these lesions where the virus mostly lives to get monkeypox. I say mostly because virus has also been found in spit and sort of respiratory secretions, as well as semen, and it is much more hardy than COVID. So we know COVID dies on surfaces pretty quickly. It took us a while to figure that out. So I wore gloves and like sanitized all my groceries for a while at the beginning of COVID. We now know it's pretty weak and gets killed pretty quickly. Monkeypox is a little stronger. So there have been cases of transmission from like bed sheets, people changing bed sheets in hospital, come in contact with some sort of pus or virus secretion and get monkeypox that way. One really good component of this transmission route is a person is not infectious until the first lesions are visible. So we have a sign that somebody has monkeypox and is infectious. We had the exact opposite with COVID, right? You might not feel sick at all for up to 2 weeks, and you could be transmitting virus that whole time. And that was a really killer for us, right? Because for a while we didn't have testing. So you could be going around feeling fine, spreading COVID all over the place and not even know it. So one major benefit to us is that these lesions really portend infectiousness. So you can know yourself and other people can recognize that this is infectious. Currently, monkeypox is mostly operating like a sexually transmitted disease. And it's mostly been in, maybe you've used this heard this clunky term in the news, the men who have sex with men community. You can say gay or bisexual men. That other clunky term is sort of used because someone might say, well, I'm not gay, but I just had sex with a man one time. So it's meant to be more inclusive, but it's just sort of awkward. And so most of the cases, we don't really know why it started here, but most have been transmitted through sexual contact, mostly because intimate contact is a lot of skin to skin contact. So even if you have a small, tiny lesion on your arm, the virus can be transmitted that way. And I want to make something really, really clear here. This isn't a disease of gay people, and it's not going to stay just in the gay community. So I feel like if you are not a gay or bisexual man, you might breathe a sigh of relief. But there's nothing special about gay or bisexual men. Anyone can get this, and there actually have been cases of household transmission now. So it's nice. There's some nice aspects to this transmission, and that like we can see when we become infectious, it's really obvious. It's not airborne. It's mostly you have to get really, really close to somebody and sort of touch their wounds. But it is not confined to the gay community. It's not a gay disease. It's going to spread beyond those confines. And I want to just compare this to COVID-19 because this was actually a really big controversy. It started out sort of a scientific controversy and became a public controversy too. In the beginning, COVID was said to be droplet transmitted, meaning like these bigger sort of spit particles that come out of your mouth when you sneeze or talk, were the only way to transmit the virus. And that's where that 6-foot rule came. These droplets largely drop to the ground quickly, and they're out of the air by the time someone is 6 feet away from you. Turns out that is not the only way COVID is transmitted. We actually know now that it's airborne transmitted, meaning it's not just in these particles. It can be in much, much, much tinier, smaller particles, and it almost acts like smoke. So you can think of like if you're standing by a fire, anywhere the smoke can get, that's exactly how this virus can move. And so that 6-foot rule, I still sometimes see the 6-foot signs some places. It really means basically nothing. And that's why we need masks, is because COVID can linger in the air for a long time. It can spread through the air. It's really an airborne transmitted virus. So you can see like airborne, everyone has to breathe air. There's a lot of air circulation. A lot of people are susceptible to COVID-19, whereas direct skin to skin contact, and largely we've seen it through sexual contact, is much, much different, and in some ways is easier to curtail. And I just want to sort of throw this up here from the American Society for Microbiology. We've had monkeypox going really for about 8 months now. It's been going really at a faster clip for about 4 months now. And if you remember, 4 months after COVID started, we were largely in a global lockdown. There were millions and millions of cases. There were tons of people who had died. There were tons of people who needed to get heart transplants, lung transplants. And so here now, 8 or 9 months into this pandemic, and this was a little bit ago, there's 30 to 50,000 cases, as opposed to the massive millions, and I'm sure at that time almost approaching billions in terms of global cases. And this is the current COVID burden, almost 300 million cases, of which about 1 million have died. Monkeypox is much, much, much less fatal. It's largely not fatal. And so only 12 people out of this almost 32,000 people have died. Most of those 12 people had other things going on, were immunocompromised, or had another sort of comorbidity. So this transmission, I think, is the most reassuring thing that you can see. There's, it's not just everywhere all the time, and there are some easy ways we can curtail it, and that's really just shown by these numbers. So transmission, easier to mitigate, and we know when someone is infectious, so we can see the infection, and that's so much different than COVID-19. The last two things I'll go through a little bit more quickly. So because of smallpox, we actually know a lot about monkeypox, and we already have tools to fight it. So let me tell you a little bit about that. So it's sort of a strange thing to say we're lucky that we had smallpox, because smallpox is a really horrible disease. I just want to remind you, my boxes got a little shifted, but monkeypox is super closely related to both smallpox in humans and this other vaccinia virus, which is in the smallpox vaccine. Here's a picture of a young girl who has smallpox. It's the same sort of like pustule lesions, but it is so much more devastating, and it has about a 30% fatality rate. Even if you don't die, it's likely you'll go blind because of these pustules. It just has a lot of morbidity and mortality, and it is a horrible disease. The one good thing about smallpox, it is the one single only disease, only infectious disease that we have eradicated from this earth. So smallpox is not transmitted anymore. It exists in a few freezers, in some science labs, but it is no longer a disease that we get. And in fact, the vaccine is no longer even given. But because it is so closely related to monkeypox, we have treatments and vaccines for smallpox that work for monkeypox. So we already have vaccines, we already have treatments. Let me tell you a little bit about those. So there are these 2 smallpox vaccines that were developed more recently. So these weren't the ones that eradicated smallpox. They're more recent. And one of them is an inactivated vaccine called Jynneos. That one, it means the virus is dead. You cannot get smallpox, or I mean monkeypox, can't get any pox from it. And it's a lot like COVID was to begin with. You get 2 doses, 4 weeks apart. It's largely very safe. There is a second one that is based on a live vaccine. So there is monkeypox in here, and you can get lesions from these, from getting vaccinated. And it's a lot more like that old smallpox technique where you get sort of the 2 needles. And if you know anyone, I can't even remember the date, but let's say older than 50, they have a smallpox vaccine scar. This is a lot more like that. So it's more detailed in how it's given, and it's not as safe as the inactivated one. So it's not safe for immunocompromised people, and there is a small chance that you can get lesions and then pass on the disease. So you need to be very careful when you get it and cover up any lesions, or stay socially distanced when you get this vaccine. Unfortunately, or fortunately, I'm not sure which way to go. We had a stockpile of these vaccines, but the one we had was this one, the ACAM 2000. So it just so happened that this real big outbreak happened in the gay and bisexual community, and where we've seen a lot of infection is in people with HIV. So they cannot take this vaccine because they are immunocompromised. So that was a big oopsie on the part of, I don't know if it was the government or who to blame for that. We have a lot of vaccine, not a lot of people can take it. There's not a lot of this one around. If you want to get vaccinated, and it is recommended for anyone who is a man who has sex with men, you can go through the New Mexico State Department of Health. It's kind of a process, but there is vaccine available. And I know people who've gotten vaccinated successfully. The one other thing about these vaccines that's a little nice is they can work as a treatment. So once you already have monkeypox, you can get the vaccine and it will reduce your symptoms and transmission by sort of giving your immune system like a good kick in the pants. So it's also nice that that's sort of a treatment. We do, though, have a tried and true treatment called TPOXX. So we don't have a lot of this in stockpile right now, so it's sort of reserved for the worst cases, but it can help shorten the infection, get rid of some of that horrible pain, swelling, pustule lesions. So that is both good news. I think I have enough time here. Yeah, I got enough time. We're going to go on sort of a side story here, because smallpox was really how the first vaccines in modern times were invented and used. And so this is a story I tell in my microbiology class. But in like the late 1700s, mid 1700s, there was this observation that it's well known that milkmaids are especially pretty. Kind of weird, but there came to be a scientific understanding of this. So here's a beautiful milkmaid going out to milk the cows. So these were young women who did all the milking. And it was hypothesized that the reason milkmaids were so pretty is they were very unlikely to get smallpox. Smallpox, is, if you survived, was a horribly disfiguring disease. So here is a young man who survived smallpox, and you can see he just has pock marks all over his face. Sometimes it could be even worse. And over here is a picture from when the first smallpox vaccine just came out. On the left is a boy who didn't get vaccinated, got smallpox. On the right, there's a boy who did get vaccinated. And I can't remember, this is sort of an apocryphal picture. I can't remember if these boys were brothers or they just lived next to each other or were friends, but you could see the vaccine worked well and you sort of missed out either on dying, 30% chance you'll die, might go blind, or you'd end up pretty horribly disfigured. And then, so going back to this cow connection, the hypothesis was that milkmaids were less likely to get this horribly disfiguring smallpox disease because they were frequently infected with cowpox. Cowpox is in the same family as the monkeypox and the smallpox. It produces these little lesions, and it's in cows. It can spread to humans, still around. The thing about this, it was much less fatal. You got many fewer sort of pustule blisters, and you largely recovered really quickly and you were fine. But once you were infected with cowpox, you were immune from smallpox. So cowpox worked kind of like a vaccine. And at this time, I can't remember which monarch it was, but someone in Victorian England said, hey, I heard sort of Eastern medicine uses this technique to keep people from getting smallpox. And it was largely her sort of making it popular that we got vaccinations. And this is how the first thing happened. So here is a doctor in the late 1700s who had been studying vaccination and infectious disease. He'd been in contact with this monarch that I can't remember her name. And what he did was he took some sort of infectious material from a cowpox lesion from this milkmaid's hand, and he used it to inoculate this 8-year-old boy with cowpox, and then he exposed him to smallpox. This was extremely unethical. Like, this boy, I think, was just some boy, child of somebody who worked on the farm, no permission. You can see the boy sort of being held down. And really, if the boy had gotten smallpox, he could have died. But Dr. Jenner showed this cowpox inoculation protected him from smallpox. So after this, there were still sort of some doubts and controversy, but the techniques we use for modern vaccines really took off. And It's the same sort of ideas we use today. So this was to protect against smallpox, and we're largely using the same sort of idea right now. I also want to tell you, this is where the term for vaccination comes with. It means like vaca, like cow. It's inoculating someone with this cowpox. So vaca, it's like basically saying vaccination is inoculating yourself with some cow disease. And so smallpox has been around a long time. We basically know how to do vaccination because of smallpox. And so we still use the same theory. So the cowpox version was a live attenuated vaccine, and this is the exact same thing. It's a live attenuated vaccine that we made to fight smallpox, just happens to work for monkeypox as well. So current knowledge and tools, we have some, that's great. When COVID came around, it's the first time we had ever seen this virus. It was novel. We didn't know anything and we had no tools to fight it. So this is a huge difference. And I want to wrap up with evolution. So I mentioned in the very beginning that coronavirus and pox virus are in these two very different families. Pox virus has DNA, where coronavirus has RNA. And RNA is very, very hard to sort of proofread when you're copying the whole genetic material. So we and all mammals and all viruses and anything with a DNA genetics has ways to check to make sure if the DNA was copied correctly or if a mutation was inserted. And we can actually correct those mutations before the cell goes on to live its own life. These RNA viruses cannot do that. So anytime a mutation happens, it's stuck there and they mutate really, really quickly. So here I'm going to show you this graph of how much genetic material an organism has, that's its genome size over here, and how fast it mutates. So way, way over here on the big size of lots of genes and lots of genetic information are animals like us, mice, fruit flies. We have a lot of genetics and we have an extremely low mutation rate. So we don't see a lot of mutations. When we do, it's bad. That's basically what cancer is, but we don't see it that often. And there's smaller, simpler organisms, bacteria, fungi that have smaller genomes. They have slightly higher mutation rate, but where we start to see these super high mutation rates are in the viruses. And the fastest, most mutating, highly evolving thing we know are the RNA viruses. So coronavirus is smack in the middle of this most quickly mutating virus that we know. Monkeypox is over here. It's almost more like any organism that we know. It doesn't mutate that quickly. So that means mutations are sort of the base ingredient for evolution, for all of that evolution we saw in COVID-19, making it more transmissible, in some cases more virulent. We just don't expect that rate of mutation in monkeypox. It's like 4 to 6 times fold lower than what we saw in RNA viruses. So that's good news with an asterisk. The current strain of monkeypox does seem to be evolving faster than the previous versions. So I'm showing you here another one of these sort of family trees. The important thing to know here is the longer these branches, the faster those viral strains are evolving. So here, all these little colored dots represent viruses from the current outbreak in the US, the UK, etc. Here's some in the US. All of these ones over here are from the old outbreaks. So you can see these new ones are very, very long branches, meaning they've evolved a lot. So we don't know exactly why that's happening, but that's probably the reason this outbreak looks different than the previous ones. These mutations probably gave it the ability to transfer human to human. We don't know what this means for the future. Is it going to continue to evolve really quickly? What way will it evolve? But at any rate, even if it continues this mutation, it is nowhere close to COVID. So we have less potential to evolve than COVID, but it does seem to be a little tricky. So we need to keep an eye on it. I'm going to wrap up in 2 minutes. I want to show you just this sort of graph that puts everything I've talked about together. So what this is showing contagiousness on the x-axis here, and that's that R naught number we discussed. Over here is the fatality by percentage. So if you get this disease, how likely are you to die from it? And if we combine those two parameters, we can really get an idea of how bad a disease is. So there's these categories of contagiousness, like not very contagious, to vaccinate now immediately, and then like how likely are you going to die, with all these different quadrants in between. So seasonal flus over here, it's pretty contagious, but you're okay. We have things like stomach bug right here, common cold, pretty contagious, but you'll probably be okay. And here's SARS, the first SARS, which was not COVID, but it's pretty closely related to COVID. It was more deadly than COVID, so COVID's actually more over here. And I would place monkeypox. We know it has between 1 and 2 R naught, and it's very, very not likely to be fatal. So I think it's pretty close, between 0 and 0.1%. So I'd put it somewhere over here in this sort of gray quadrant, where it has some ability to be spread, but overall it's not wildly bad. It can be a horrible disease to suffer from. It's quite painful, it takes a long time to get better from, but I don't see it like ending up somewhere like a smallpox, a tuberculosis, Ebola, whooping cough. Over here, its position over here really suggests it's containable, it's limitable, and it's not going to be a pandemic, at least not like COVID. And here's just sort of a wrap up to give you some peace of mind. Here you can see all of the different sort of variants that have emerged from COVID-19. There's only 2 variants of monkeypox. And again, COVID is spread either through respiratory droplets or airborne. And this really requires much more direct contact for transmission. So I'm going to stop there, and I'm going to go back over here to sort of this wrap up slide. And I think we have about 10, 12 minutes for questions. So if you have any questions, I would be happy to answer them if you want to shout them out or put them in the chat. And thank you very much for listening to this important public health message.
Hello, Dr. Garcia.
Hello.
I wanted to ask a question about the coronavirus. I know it hasn't been decided yet, and there's been a dispute or controversy as to whether it came from a lab or if it jumped from animals. So what's your thinking on that?
Yeah, my thinking on that is complicated. I think it's going to be really hard for us to know. When this first happened, I heard the lab theory and I was like, that's a conspiracy theory. People need to knock that off. And I hate that. But there is a lot of evidence that that's a possibility. Not that it was created in a lab, but Wuhan just happens to be home to the Institute of Virology, which houses a bunch of viruses that were collected from bats. Some of the first people to get sick were people who worked at that institute. You may have also heard there were some of the first cases were linked to a meat market. Only about half of the first cases were linked to that market. And we haven't found any animal that serves as a definitive first host. So I'm going to sort of just put those pieces of evidence out there. I don't know if we'll ever know. And I really, 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 really hope it didn't escape from a lab. It's a possibility. It is possible that it just came from an animal. We saw that happen just like 15 years previous with SARS. So I don't have an answer. I don't know if anyone ever will have an answer, considering we need data from China. But thanks for asking that question. That's still a really good question that we should explore. Well, if there's no other questions, I'd like to just say thank you again. If you do have questions, feel free to stick around. And thank you so much for listening again.
Thank you, Dr. Garcia.
Thank you.
All right, thank you for everybody attending. If you guys are in